Hey, it's Ashmeet. Welcome back to the Scribbled equation. Quantum mechanics is weird, to say the least. It goes against common sense and says things like you can be in a quantum superposition of being both here and there at the same time. If you're Schrodinger's cat, you can be both dead and alive at the same time. You can also be quantum entangled with electrons in the Andromeda galaxy, for example, what Einstein called as a spooky action at a distance. There is another very famous and equally counterintuitive idea called the Heisenberg Uncertainty principle. Now, to be fair, it's not a trademark of quantum mechanics exclusively. It's got more to do with Fourier transforms, if you will. It just so happens when you express position and momentum as quantum variables, they turn out to be a Fourier pair. But hey, that's for another day, another video. Now, typically, quantum phenomena are often associated with the microscopic, the small, the atomic scales. And there are many reasons why that is a good rule of thumb. Same goes for Heisenberg. Most things around us are massive enough, and the Planck's constant h is small, so that we don't experience it in our everyday lives. But today, we are talking about a macroscopic experiment where Heisenberg's principle comes to life. And we also scribble a few equations and derive it as we go along. So make sure you simultaneously subscribe and watch till the end with complete certainty. Let's get started. Heisenberg's principle puts fundamental limits on simultaneous knowability, more like simultaneous existence of position and momentum of any particle. You just can't know both where the particle is and how fast it is moving in a precise way at the same time. And no, it does not depend on how good your ruler or your speedometer is or how smart you are. It's a fundamental limit in nature, and it says that the product of the uncertainty in the position of the particle times the uncertainty in its momentum is lower bounded by the Planck's constant up to order 1 factors. To know two quantities precisely and simultaneously, our uncertainty for each would have to be 0, and therefore for the product as well. This is exactly what Heisenberg says is not possible for x and p. The better you know one, the more uncertain you are about the other. Okay, so where can we see this? We've all probably seen or heard about diffraction of light. It's the tendency of light to bend and spread around obstacles. It's what causes light falling on a CD or a DVD to diffract into those rainbow-colored patterns. The famous single slit experiment beautifully showcases diffraction. Say, light of a certain color is incident on a giant 2D plane with only a thin, narrow slit for it to pass through. We'll call the slit width as W. What happens next is then observed on a screen far away. Let's call this direction towards the screen as X, and the width of the slit is in the Y direction. Now, if light were made of a bunch of classical particles, like billiard balls, the incoming momentum P0 will purely be in the X direction. Only a subset of these particles, which are aligned with the slit, are able to go through with no change in momentum. They would continue their journey in a straight line along the X direction and would just create a bright spot of width W on the screen. In this case, I would have known both where the particles are and precisely know their momentum, which is in the X direction. Classical determinism. But light is not classical. What we actually see is that it spreads around the slit and is found all over the screen with a very peculiar pattern of bright and dark fringes. This is where advocates of the wave model of light come in and say, hey, light is a wave. And every point in that slit acts as a source of secondary wavefronts, which then go and interfere and superimpose on the screen. If mountains match mountains in the oscillation, you get constructive interference and correspondingly a bright fringe. If mountains align with valleys, you get destructive interference and a dark spot. This model amazingly explains the diffraction pattern which has a central maxima and tells us that the location of the dark spots are given where the sine of this angle theta is an integer multiple of the ratio of the wavelength of the light to the slit width W. The central maxima contains most of the brightness, so it's a good measure of how spread out the pattern is. Sine theta for these dark spots is inversely proportional to W. So as you can see, if I make the slit narrower, the pattern spreads out more. On the other hand, the larger the slit, the more concentrated the pattern is. Very counterintuitive from a classical particle picture. But then again, quantum tells us that light has a wave-particle duality. Another way to think about this is that for these particles of light, photons, to spread across the screen, they must have had some component of momentum in the y direction. So, some of the incoming momentum, which was purely in the x, gets transferred into the y direction. More spread the pattern is, the larger the y momentum of the photons that reach there. If I make the slit narrower, the spread in the possible y momenta becomes larger. Many of the photons, which stay concentrated near the central bright spot, will have to have a small py. But the ones that go further out will have had to have a larger py to make the spread. The better I know where the light passed through, the less certain I can be about its y momentum. Let's work it out further. For a simple back-of-the-envelope calculation, let's focus on the small angle approximation, where we can take sine theta to be approximately theta. This gives us that the angular width of the pattern is of the order lambda over w. Just for calibration, even at theta about pi over 6 or 30 degrees, the error is only around 5%. So it's a good approximation if we assume that w is only somewhat larger than lambda. And true to our spirit of scribbling, I will stick with loose approximate equalities to capture the broad dependencies. The incoming momentum P0 is all in the x, and de Broglie's hypothesis tells us it connects with the light's wavelength. P0 is h over lambda. After diffracting through the slit, light has some momentum in the x and some in the y, and we can get these two components as a function of the angle. Px is P0 cos theta and Py is P0 sin theta. At the first dark spots, sin theta is lambda over w, which is much smaller than 1, and cos theta is approximately 1 to leading order. So the x momentum is still approximately P0, h over lambda, while on average, y momentum is 0 since the pattern is symmetric about the center. The larger y momenta are of the order of P0 lambda over w. That is, Py is spread roughly from minus to plus this number, which is exactly the uncertainty in the y momentum. Combine this with de Broglie, we get that delta Py is of the order of Planck's constant by the slit width w. But hey, what is w again? It's just the uncertainty or the spread delta y of the position where the photon might have gone through. All we know is that it went somewhere through the slit. Rearrange this and we find that the product of the uncertainties in the y position and the y momentum are of order Planck. Exactly the stuff of Heisenberg's uncertainty principle. So there you have it, a macroscopic experiment which so beautifully captures the limiting conditions of nature. The more localized a particle is in position, the less localized it'll be in momentum space. Sounds familiar? That's because it's precisely the Fourier transform. I can do a more in-depth analysis of the entire intensity profile of the diffraction experiment and connect it with the Born's rule, the probability of finding the particle at various locations, how that connects with the classical and the quantum side of things. Let me know in the comments if you'd like me to do a much more deep dive in an upcoming video. In Heisenberg's principle is not just an insight into the fantastic fabric of reality, but also a life lesson. The more you try to contain something, the more it pushes back out. So be like light. work around the obstacles, think outside the confines, and constructively interfere with the good. Keep scribbling, and I'll see you next time.